Hello and welcome to my third video on the lecture series on Chemistry 111. Today we plan to discuss components of matter. So let's just jump into it. Matter, as we all know, is anything that has mass and occupies space, i.e. has a volume. So that's matter. Matter itself, we do know that it exists in three physical states, namely solids, liquids, and gas. The fourth state of matter is plasma, which is charged gas particles, which is usually seen in the cosmos and in the space. Of course, the solids, liquids, and gases differ mainly on their particles, how they move, and what's the distance between the particles. Matter, we can say, exists in two major forms, either as mixtures or as substances. The main difference between the two is when it exists as mixtures, it consists of two or more components and they are in variable proportions. For example, if I'm mixing sand and iron filings, that mixture could vary from day to day, from person to person. I may mix more sand and less iron filings, and you may mix more iron filings and less sand, but ultimately it is a mixture of sand and iron filings. The proportions of each one of the components may vary in case of a mixture. Okay. In case of substances, on the other hand, they are containing fixed composition. They have fixed composition throughout. Now that could be consisting of either elements or compounds, but they have the same composition throughout in case of these substances, whereas in mixture you have two or more components and they have variable composition. The other difference between the two is that because mixtures have these variable components, each component will retain its property. Okay, so the mixture displays properties of components. So in our example of mixture of sand and iron filings, if I move a magnet over that, it will attract the iron filings. So although the mixture has two or more components, each component will retain its property, and the mixture therefore will display properties of all of its individual components. In cases of mixture, we further divide them into either heterogeneous mixtures or homogeneous mixtures. Now, homogeneous mixtures are also called as solutions. Of course, the difference between the two is in a homogeneous mixture, you are not able to see the individual components. The two components of the mixture mix throughout, and you're not able to visually see those two components separately, and they will have the same composition throughout, similar to a substance. So in homogeneous mixture or a solution, there are no visible parts, and it has the same composition throughout. So if I take a solution of salt water, so you take a glass of water, dissolve salt in it, and mix it up thoroughly, and the salt completely dissolves in that glass of water, that's a solution, and the composition of that solution at any position in that glass of water will be the same, and you cannot visually distinguish between the salt and water. Whereas heterogeneous mixtures are, you're able to see the parts individually, so visible parts, and of course because of that there will be differences in the regional composition. So let's take our example of the sand and iron filing. You will be able to visualize the iron filings and the sand separately, even though they are mixed. And if you take a sample of that mixture at one spot, you may get a particular proportion of sand to iron filing, and you sample that mixture from some other region, you will get a different composition. So composition will vary from region to region, from various areas within that mixture. So that's a heterogeneous mixture and a homogeneous mixture. Okay, and then of course these can be separated, mixtures can be separated by physical means. So all mixtures are separated by different physical means into their components. And this physical means can be of various types. You can simply filter them, filtration. You can evaporate and crystallize, for example salt water, crystallization. Distillation, which is based on different boiling points of the components, especially in a mixture of liquids, or based on their weight and their mobility in electric field, you can separate them using chromatography. So all these are physical means of separating a mixture. On the other hand, substances are having fixed composition throughout, as we said, and these are divided into two types. Either they're elements or they're compounds. Elements are substances which are composed of one type of atom. Okay, that doesn't mean that element should have only one atom. For example, carbon will have one carbon atom, whereas oxygen exists in a diatomic molecule state. So oxygen is O2, chlorine is Cl2, fluorine is F2. So these are composed of one type of atoms. Although oxygen has two oxygen atoms, but both the atoms are the same. So it is composed of one type of atom. They are of course classified as, and we'll see more when we do the periodic table, metals, non-metals, and right in between them are metalloids, which have some properties of metals and some properties of non-metals. And atoms, of course, are the smallest particle of the elements which retain all the properties of the element. So atoms are smallest particles of the element which retains all properties of the element. Now remember, we do know that atoms contains subatomic particles. So definitely atoms are not the smallest particles, but they are the smallest particles which retain all the properties of that element. So once you go to subatomic particles, those properties are different from those of the elements itself. And atomic mass in cases of elements is simply an average of their isotopic masses. So atomic mass is the weighted average of all isotopes of that element. Okay, so we'll talk about what is isotope in a minute once we do the structure of atoms, but this is what you need to understand about elements completely, that they are composed of one type of atom They are classified as metals, non-metals, or metalloids. Atoms, of course, are the smallest particle of an element retaining all its properties. And any elements, when you look at the mass of the element, that element can exist in various isotopes, and you take a weighted average of all the isotopes, that will give you the atomic mass of that element. Therefore, you will often see atomic mass as decimal numbers. Let's move on to compounds. Compounds are consisting of two or more elements. And these are, of course, the elements are combined in definite proportions or fixed proportions by their masses. What I mean by this is a compound like, say, example, water. It consists of two elements, hydrogen and oxygen. And in that case, two atoms of hydrogen combine with water to form, combine with oxygen to form water. It doesn't matter whether you find water on moon or on earth, water is always going to consist of the same two elements combined in the same proportion, 2:1 of hydrogen to oxygen to form water. So that's the meaning of this first statement, that compounds consist of two or more elements, but those elements will always be combined in the same ratio by their masses. The other important thing is mixture also has two or more components, but the difference is between a mixture and a compound is the mixture will show properties of both of its components, whereas the properties of a compound will differ from its component elements. Okay, so it shows new properties. So properties differ from its component element. This is different than the mixture. Okay, and in this case, of course, the molecular mass just like we talked about atomic mass, molecular mass is simply the sum of its atomic masses of the elements. Okay, so these are the major differences between different types of matter, mixtures, substances, elements, and compounds. Elements and compounds can only be separated by chemical changes. So we talk quickly about a little bit about atoms. Again, a quick overview about atoms. Um, we know that atoms' mass is concentrated on a tiny region called the nucleus. And that nucleus contains of neutral particles called neutrons and positively charged particles called protons. And that's the nucleus. The diameter of the nucleus is very small compared to the diameter of the atom itself. So I'm just going to, I didn't draw this accurately enough. Let me be sure that the nucleus is in the center and you have the atom around it. Now the diameter of the atom, which basically has extra nuclear space here, and that extra nuclear space is where you have electrons. Now we will talk a little bit about various theories about how the electrons are distributed around the nucleus. Are they in specific orbits like this, or they're just in a cloud? But any case, electrons lie outside the nucleus and they are negatively charged. J.J. Thomson, through his cathode ray experiments, was able to prove the existence of electrons and that they were negatively charged. Subsequently, mass of the electron was discovered by the famous Millikan's oil drop experiments. Then Rutherford suggested his famous plum and pudding model to explain the structure of atom, where he thought that the nucleus actually was in the form of a pudding with positively charged in the pudding, and the electrons being negatively charged like raisins in the pudding. At the end of the day, for electrons, what you need to understand is that they are pretty much uh, negligible mass. So they are almost weightless and they have a negative charge. The nucleus have neutrons and protons, their relative mass as compared to electron is considered as 1. So relative mass, you don't have to remember the detail exact what the mass is in grams, but relative mass meaning related to electron. Relative mass is 1, each one of them. And charge for a neutron is 0, whereas charge for a proton is positive. So we represent electron with a minus charge, a proton with a positive charge, a neutron with a zero charge. So this is main concepts about atom, the different parts of the atom. Um, you may want to read a little bit on cathode ray experiments. You may want to even read the experiment done by Thomson, who discovered mass to charge ratio for electron, and of course Millikan's famous oil drop experiment to discover the mass of electron. And then the famous Thomson's plum and pudding model, where he believed that the entire atom is like a sphere. So this is what Thomson believed. Where the entire pudding itself is positively charged, and you have electrons embedded in this positively charged uh, pudding as raisins. So that was his plum and pudding model of Thomson. We know this is wrong. And then, of course, Rutherford came up with his gold foil experiments, showing that the mass of the atom is focused on a very small area called nucleus, and the empty space around the nucleus is where the electron exists. And of course, then there was Bohr's theory, who thought about atom like a solar system, with the central nucleus being the sun and the electrons moving around the nucleus in various orbits. This theory is okay to understand, but doesn't explain all the behavior of electrons. And now the modern theory, of course, is the theory where we believe that the electrons behave like particle and wave, and there is the central part of the atom called nucleus, but the electrons are around the nucleus in a cloud-like fashion. They move like waves around the nucleus, and it's we talk in terms of probability of finding an electron at a particular position around the nucleus. So this is all the various theories of atom. Let's move on to details about atomic number and the structure of the atomic number and others, atomic mass and other concepts. So let's just start with a symbol. The all elements are displayed by a symbol, for example, like this, X and A and Z. The A at the top is the atomic mass number. The Z is simply the atomic number. So let's take each one of them. First and foremost, what you have to understand about the Z is that it is called as the atomic number, and that is simply the number of protons in the nucleus of that element. The importance of Z, the atomic number, is that for a given element, Z is the same. Meaning, if I have, for example, an element like, say, carbon. Okay, carbon has an atomic number of 6. Okay, so the Z in carbon is 6. It doesn't matter, as long as it is carbon, it will always have a Z of 6. So the atomic number is very unique to a particular element, and it is based on the atomic number that your periodic table is organized. So when we talk about the periodic table, the elements are arranged in from left to right, and they keep going in a periodic manner, keeping on getting arranged with progressively increasing atomic number, meaning increasing protons in the nucleus. So that is Z. Whereas A, which is the atomic mass number, is simply equal to the sum of neutrons plus protons in the nucleus. So if I have two elements, so for example, if I have carbon, which can exist as 12, 13, and 14 carbon, and each one, as I said, because all three are carbons, they will have the same Z value, which is 6. But their A values are different, as you notice, 12, 13, and 14. So what we mean by this is, if you see the number of protons in carbon will be 6 in each one of those cases, because Z is the number of protons. Whereas number of neutrons, which is nothing but A minus Z, meaning A is the sum of protons and neutrons, and Z is the proton. So when you subtract n plus p minus p, you get n. So in this case, it will be 12 minus 6 equal to 6. So 12C6 will have 6 protons and 6 neutrons, whereas 13C6 will have 6 protons and 13 minus 6 or 7 neutrons. And 14C6 will have 6 protons, but the neutron will be 14 minus 6, which is 8 protons. So these three are called as isotopes of carbon. So isotopes are atoms of the same element. So we're talking about the same element, and therefore having same atomic number, or Z, but differ in their neutron numbers. They differ in how many neutrons are there, neutron numbers. Okay, so those are isotopes. Therefore, we talked about atomic mass. So, for example, if we say that this 12C6, and I'm just giving an example here, this may not be accurate, but let's say, for example, the 12C6 in Earth has an abundance, meaning how much it is found on the Earth crust. Say this is, say, 90%. This is, say, 6%, and this is, say, 4%. And the weight of this 12C6, again, I am giving hypothetical numbers here just to elicit my point here. So let's say the atomic weight of each one of these isotopes is different, and say this isotope weighs 11.90 atomic mass unit. This isotope weighs say 10 atomic mass unit, and this isotope weighs 14 atomic mass units. Right away, you should be able to judge that because the commonest isotope is this one, 90%. So your average weight, so your atomic mass of our hypothetical carbon will be an average of these three isotopes. But because the 12C6 is most abundant at 90%, your average will be nearer the 11.90 AMU. So let's do a weighted average. So you have weight of 11.90 AMU. You multiply that by the 90%, which is 0.90, plus your weight of the 13C6 is 10 AMU. You multiply by its abundance, which is 6%, which is 6 is percent is 0.06, plus 14 AMU for the 14C6, and its abundance is 4%, so 0.04. So if you do the mathematics on that, the calculation on that, you will get 11.9 multiplied by 0.90 is 10.71, plus the 10 multiplied by 0.06 is 0.6, and then you multiply your 14 by 0.04 is 0.56, and you add up all of them, the 10.71 add to 0.6 and 0.56, you get 11.87 AMU. So that would be the atomic mass of carbon, taking into account each one of the isotope. And you notice that the final average atomic mass of that carbon is nearer to 11.9 because the 12C6 isotope is the most abundant. Okay. In the exam, the questions can be asked on isotopes in various ways. So let me write down here questions on isotopes. Okay. So one, of course, is you need to know the definition. So MCQ on a definition of isotope, which simply means isotopes are atoms of the same element, so they should have the same number of protons or Z value, but they have different A values, which is different number of neutrons. The second type of question that can be asked in isotopes is they will give you the abundance of, so as we gave you example, is find the atomic mass. Now don't get confused between atomic mass and atomic mass number. Atomic mass number is the number of protons plus number of neutrons. Atomic mass is the average, weighted average of all the isotopic masses. So find the atomic mass of, say, carbon, which has 3 isotopes, so 12C6, and they'll give you some weight, as we gave in our example, some hypothetical weight, so 11.90 AMU, and they'll give you its abundance is 90%. Another isotope of carbon, 13C6, they'll give you its weight, say 9.00 AMU, and they'll give its abundance, say 6% abundance. And another isotope, 14C6, having a weight of, say, 14 AMU and abundance of 4%. And then you just do the weighted average to get the atomic mass. So that's the second type of question. The third type of question that is asked, which is interesting, and they may give you the average atomic mass and give you the masses of individuals. So for example, they may say the atomic mass of, say, an element X is 20.1 AMU. Okay, this atomic mass. It has 2 isotopes. Okay, and the masses of each of the isotope. So one isotope is X, say 10, and the mass of that is given to you as 22.1 AMU, and the mass of a second isotope, 11X, is equal to 18 AMU. And then in MCQ they'll give you various percentages. So what is the abundance of the isotope of with a mass of 10, mass number of 10, and they'll give you various options, A, B, C, D, and again various percentages will be given to you. Okay, so the problem will be 2 of the things you can eliminate quickly. So for, again, I'm giving this as an example, so I may not be accurate in my calculation, but I'll make a point here. Is say for example, they give you 90%, 80%, 10%, and 25%. Okay, so now looking at the problem, you will notice that the 10x is 22.1 and the average is 20. So this 22.1 is pretty, oh, I should make it even more dramatic so that I drive home the point correctly. And let's just make this as 20.9 or something like that. So you will notice that this 10, the isotope with 10 mass number, uh, weighing 20.9 is pretty close to 20.1. So you will know that this is the most abundant. So you could guess that either it could be 90% or 80%. For sure, it is not 10 or 20%, 25%. Okay, but then the problem is you're stuck choosing between 90 and 80 and guessing what it is. The way I like to solve that problem, again, these numbers may not be accurate, but the way I like to solve the problem is let X be the abundance of the isotope 10X. Therefore, the abundance of the other isotope will be 1 minus X in terms of, if you take the total abundance as 1, so this in decimal numbers rather than percentage. And then you take the average. So you know that 20.1 is the atomic mass of X. And if you say that the 10X, which is weighing 20.9, has an abundance of X, and the other one, which is weighing 18, has an abundance of 1 minus X, you can actually mathematically solve it. And therefore, what you will get is 20.1 minus 18, 2.1, taking 18 away from both the sides and then doing the math for the x's. The 20.9 subtracted by 18. Oh, sorry, I didn't do it right on my calculator. So 20.9 subtracting 18 from it, you get 2.9 x. And therefore, x will be equal to 2.1 divided by 2.9, which will be 0.7241 or something like that, and the percentage therefore would be roughly equal to 72%. So if I am forced to choose an answer between 90 and 80, I will choose the 80 for the 10x isotope. Okay, so I hope you are clear about the question that can be asked on isotopes. All right. So we talked about atomic number, we talked about atomic mass number, we talked about atomic symbol, isotopes. That pretty much sums most of the topic here, and I think I'll pause here. So let's just quick summarize what we did today. So what we did today was talking about components of matter, and we said matter is anything that occupies space and has a mass. Three-phase physical phases of matter: solid, liquid, gases. Some textbooks talk about plasma as charged gas. Masses come in two flavors, either mixtures or substances. The major difference between them is mixtures have two or more components, and these are of variable proportions. So the components are mixed in various ratios, whereas substances will always have the same components mixed in the same ratio. So it's a fixed composition. Mixtures, because they have two or more components which are not physically, they're not chemically mixed, they are just physically mixed, the mixture will display properties of each of the components. Mixtures are of two types: heterogeneous mixtures, homogeneous mixtures. In heterogeneous mixture, I can visually see the components, whereas in homogeneous mixture I cannot see the components, and therefore in homogeneous mixture called solutions, the composition of the solution is same throughout the solution, whereas in heterogeneous mixture, because I can visibly see the components separately, those components can be mixed in various amounts, and therefore they will differ in their regional composition. Of course, mixtures can be separated by physical means. Substances are of two types, either the elements or compounds. Elements are composed of one type of atom, and the reason we use that definition is, although oxygen is an element, but it's a diatomic element, so it exists as O2. Chlorine is Cl2. So it doesn't matter whether they have composed of one or two atoms, but the atoms will be the same. So elements have the same one type of atoms. The atom itself is the smallest particle of an element which has all the properties of that element. And atomic mass is the weighted average of all the isotopes of that element, and we'll talk about isotopes in a second. Compounds, of course, have two or more elements, and these elements, by the law of definite proportion, are combined in fixed proportion by masses. We give example of water. Water will always have two parts of hydrogen, one part of oxygen. Doesn't matter whether you're talking of water on Earth, Moon, Mars, doesn't matter. And compound, unlike mixture, will have completely new properties different from its components, unlike mixture, which shows properties of all of its component. And the molecular mass of a compound is sum of all its atomic masses. We talked about the structure of atom, the central part being nucleus, where the entire mass of the nucleus is concentrated. The nucleus diameter is actually very small compared to diameter of the atom, which is almost 20,000 times larger than the diameter of the nucleus. Um, Nucleus, of course, has neutrons and protons. Neutrons are neutral and protons are positively charged. The relative masses of neutron and proton compared to the electron is 1, meaning neutron, if it weighs 1, proton will weigh 1, and electron will weigh 0. You don't really have to know the exact masses. All you need to know is that proton is positively charged, neutrons are neutral, and electrons are negatively charged. And the neutron and proton will have masses of 1 each compared to electron, which has a mass of 0. I would leave it to the students to read a little bit about the discovery of atoms. I just briefly touched upon the cathode ray experiments, which led to discovery of electron. We talked about Millikan's experiment, which led to the discovery of the mass of the electron. We talked about Thomson's plum and pudding model, saying that according to Thomson, the positively charged nucleus is like a pudding, and the plum pudding, and the electrons are like raisins embedded in that pudding. Uh, Rutherford's gold foil experiments led to discovery of nucleus with a large empty space around the nucleus. Bohr's theory, of course, talks about the nucleus in terms of the atom in terms of a solar system arrangement. The sun in the center is the nucleus, and the electrons moving around the orbit around the sun. We also know that that theory itself is also not accurate, and the modern theory is that the electrons behave like both matter and particles and waves, and basically we talk in terms of probability of finding the electron or electron cloud around the nucleus. We talked about the atomic symbol of elements. They are represented by X with A and Z. The A is the atomic mass number and the Z is the atomic number. Z is very characteristic of every element. It is a number of proton that does not change, whereas atomic mass number is the combination of protons and the neutrons, and A can vary depending on what isotope you're talking about. Atomic number is important because that defines the element, and based on that you arrange in your periodic table different elements on increasing atomic number. Isotopes we spoke about, they are atoms of the same element, therefore they should have the same atomic number, i.e. they should have the same Z, but they will have different atomic mass number, that means different number of neutrons. So I gave an example of 12 isotope of carbon, the 13 isotope of carbon, the 14 isotope of carbon, but they're all carbons, so they will all have the same number of protons of 6, but the neutrons will vary 6, 7 and 8. We talked about how to calculate atomic mass of any element, which is a weighted average of all its isotopes. We talked about various questions that can be asked of isotopes. I would prefer solving the actually abundance problem in terms of x and 1 minus x, and that will give you the exact number to choose from in the multiple choice question. And that's all I have for you today. Hope I'll see you in the next video. and thank you.